When a polished metallic surface is subjected to immense pressure, it visibly warps and bends without immediate fracture. This macro-scale response originates from a complex relationship between microscopic atomic bonds and the mechanisms of material yielding. To understand this behavior, we must derive the mathematical bridge connecting atomic-scale deformation to the reinforced structures of polycrystalline microstructures. This relationship is defined by three distinct stages of work hardening. Deformation begins with Stage 1 easy glide, transitions into rapid linear hardening in Stage 2, and reaches a saturation stress during the parabolic hardening of Stage 3. These stages are sensitive to thermal conditions. As temperature increases, critical resolved shear stress decreases as heat assists dislocation cross-slip. Conversely, decreasing stacking fault energy widens faults, suppressing cross-slip and forcing the material to stay in the high-stress Stage 2 regime for longer intervals. Unconstrained single crystal deformation is characterized by high sensitivity to these external thermal variations and internal structural energy states. Mapping these physical forces requires an analysis of a single crystal under an external axial load, where the slip plane serves as the primary vector for deformation. This model relies on two specific angles: phi, the angle between the axial load and the slip plane normal, and lambda, the angle between that load and the direction of slip. Normal stress is axial load divided by area, adjusted by the cosine of phi. Projecting this onto the slip direction using the cosine of lambda yields the critical resolved shear stress. Their product, the Schmid factor, must reach a specific threshold to activate slip. Under this framework, sample crystal yielding is a geometric sorting problem, where deformation initiates once the most favorably aligned slip system reaches the required Schmid factor. While theoretical models allow for unconstrained slip, physical tensile testing involves grips that fix the ends of the crystal in place. Because the grips prevent free lateral movement, the crystal planes must undergo a combined state of bending and rotation toward the tensile axis to maintain their physical alignment. This rotation continuously changes the surface length of the crystal from L0 to L sub I, necessitating a dynamic calculation of shear strain throughout the process. As these dimensions shift, the changing slip direction angles continuously redefine the resolved shear stress required to sustain deformation. Even in an isolated single crystal, boundary constraints impose a continuous geometric reorientation during plastic flow. To track these rotating angles and plane normals in three-dimensional space, we utilize stereographic projections. This allows us to map the trajectory of the load axis, point P. As rotation proceeds, point P migrates along a great circle path toward the primary slip direction. When the load axis reaches the symmetry line, Schmid factors for primary and conjugate slip systems equalize, triggering alternating slip. This active primary slip increases conjugate resistance, a latent hardening that forces the load axis to overshoot the boundary before stabilizing. Internal friction and latent hardening dynamics fundamentally alter the expected trajectory paths before a deforming crystal achieves structural stabilization. Moving from an isolated crystal to a dense polycrystal introduces physical confinement, where individual grains are rigidly constrained by their neighbors. These grains must satisfy the condition of strain compatibility. They must deform identically at their shared boundary to prevent the voids or fractures that would otherwise break material continuity. To accommodate an arbitrary three-dimensional strain state while maintaining this compatibility, the von Mises criterion requires a minimum of 5 independent slip systems to be active. Mathematically, this is derived from the small strain assumption. Since plastic deformation preserves volume, the sum of the principal normal strains must be 0. If we examine the standard strain tensor matrix, we begin with 6 independent components of deformation. Applying the volume invariance condition lets us express one diagonal component as the sum of the other 2, reducing the required independent slip systems to exactly 5. This requirement for 5 systems is the direct mathematical result of volume conservation during plastic flow. The necessity to activate 5 systems simultaneously forces grains to utilize less than ideal slip orientations. This geometric restriction creates an additional resistance to deformation known as texture hardening. We bridge microscopic physics and macroscopic yield strength using the Taylor factor, M. Averaging 3.06 for FCC and 2.75 for BCC structures, this factor ensures a polycrystal's yield stress is always higher than the critical resolved shear stress of its grains. The red polycrystal curve shows a higher stress requirement and faster hardening rate than the single crystal black curve. The Taylor factor scales these curves, multiplying the vertical stress by 3.06 and dividing the horizontal shear strain by the same factor. Macroscopic material strength results from the structural geometry of the grain network scaling the baseline atomic bond strength. Single crystals undergo free geometric rotation, while polycrystals are restricted by strain compatibility. While isolated crystals rely on limited slip systems defined by Schmid's law, polycrystals require at least 5 independent systems to satisfy the Taylor relation. This strength stems from the fact that these nearly random slip systems must satisfy the restrictive continuity conditions of plasticity through geometric cooperation. The mechanical strength of structural metals is a byproduct of these microscopic geometric constraints.